Assalamu alaikum one more time. We're back with another video lesson. In the previous lesson, we talked about standing waves, yeah? And of course, we said what happens when two waves move in opposite direction in the same medium. Of course, if their displacement were above the equilibrium, the interference is going to be constructive, and if it is below the equilibrium, it is going to be destructive. And of course, these are one of the things we've mentioned. Then after that, we've covered standing waves, yeah? So what were standing waves? Of course, we said standing waves happen when, or the result of two waves, when these two waves are moving, passing in a given medium. But remember, in order for standing waves to happen, the two waves must have the same frequency, same wavelength, and the same amplitude as well. And as a result of this, of course, we get a pattern of constructive and destructive interference. In another word, we get nods and antinods. We said nods is a point where on a standing wave where the displacement is zero, yeah? And then antinod is a point on a standing wave where the displacement is maximum, yeah? And of course, we said in a standing wave, the amplitude is twice of the displacement of the individual waves. And of course, we gave some examples and all that. And then we ended up at this point here, yeah? Okay, now let's go through these standardized test preparation. Okay, so of course we have multiple choice questions. The first one says, base your answers to questions 1 to 5 on the information below. So we have this piece of information for question 1 up to 5. Use this diagram to answer the question, okay? So here's what we have. It says a mass is attached to the spring and moves with a simple harmonic motion on a frictionless horizontal surface as shown above, yeah? So the first one says, in what direction does the restoring force act? Now we do know that, okay, when it comes to mass spring system, all right, we know that, let's say, if I redraw this one here, let's say if this is the equilibrium, where x is 0 here, the displacement is 0, then if the mass is stretched to this side, if the displacement is to this side, then of course the restoring force would be in opposite direction. But if the spring, for example, were compressed, then that means the displacement is towards this side, then the restoring force would be towards the other side here. So do you know which side is the spring, whether if it is compressed or stretched? The answer is no, yeah? So can we say it is to the left, right? The answer is no. Can we say it's to the right? The answer is no, yeah? In order to be able to answer, you say to the left or to the right, depending on whether the spring is stretched or compressed. So once again, in which direction does the restoring force act? Of course, in order to do that, or to answer this question, you need to know whether it is compressed or stretched. Then we can tell. So the force will act to the left or to the right. It depends on whether the spring is stretched or compressed. So which we cannot tell here. Can we say it is perpendicular to the motion? Obviously not. Now the second one says, in what form is the energy in the system when the mass passes through the equilibrium position? So once again, it says the mass passes through the equilibrium position. So what type of energy do we have? Now once again, if this is the spring here, let's say if it is stretched or compressed, let's say, and this is the equilibrium position here, okay? So at this point here, it is stretched, so we can see that the energy would be elastic potential energy here. If it is compressed, it is going to be elastic potential energy. But if it is at equilibrium, or if the mass passes through the equilibrium, then that means the spring is neither stretched nor compressed. And if it is not stretched or compressed, can we say the energy is elastic? The answer is no. So, but we do know that when it is passing through, that means moving through. And if it is moving through the equilibrium, that means the energy would be the energy of movement, which is going to be kinetic energy. So what are the options that we have here? Is it the elastic potential energy? The answer is no, because the spring at equilibrium, it is neither compressed or stretched. Is it gravitational potential energy? The answer is no, okay? Is it kinetic energy? The answer is yes, because the object, even though it is passing, or even though it is at equilibrium, but it is moving, it is passing, yeah? It is bouncing at this point, or in this particular, at this instant, the object is still or in motion, so of course the energy is going to be kinetic energy. Is it a combination of two or more of the above? The answer is no. Okay, now, sorry for that. Now, question 3 says, In what form is the energy in the system when the mass is at maximum displacement? Now this is obvious, yeah? When the mass is at maximum displacement, that means the spring is stretched in this case. And you do know that if the spring is stretched, then of course the energy is, of course, it is elastic potential energy. If this is x0 or equilibrium, then at this point the spring is stretched here, so the energy here is going to be elastic potential energy here. So at maximum displacement, it is elastic potential energy. Is it gravitational? No. Is it kinetic energy? No, because you'll be stretching the mass and holding it, yeah? So it is elastic potential energy. Is it a combination of two or more? The answer is no. Okay, the next one says, which of the following does not affect the period of the mass spring system? Now, the question is about the period, and it says which one does not affect, yeah? So, in order, or before looking at the choices, or before you answer this, write the equation for the period for the mass spring system. It is mass spring system, okay? So it is 2 pi, the square root of what? Of mass over the spring constant. So, which of the following not or does not affect, yeah? Can we say the mass does not affect? The answer is no, because there is a mass in the equation. What about the spring constant? It is in the equation. What about the amplitude? It is not in the equation, so this one will not affect the period. All above, that is not correct, of course. Now, for question 5 says, if the mass is 48 kilogram and the spring constant is 12, what is the period of the oscillation? Use the equation, plug in the numbers. So the mass is 48, the spring constant is 12. Plug in all this and do the math. Of course, you will get 4 pi second. Why second? Because it is the period, and this is the correct answer, as you can tell here. Okay. Now, base your answers to questions 6 to 9 on the information below. So again, now for questions 6 up to 9, use this information to answer the following questions, of course. So it says, you can see that there is a pendulum, right? A pendulum bob hangs from a string and of course moves with the amplitude of with a simple harmonic motion as shown above, yeah? What is the restoring force on the pendulum? Now, the restoring force on the pendulum, remember this, if this is the pendulum, we did mention or went through this, yeah? Of course there is mg, yeah? Or fg you can see, here is tension, yeah? So ft or tension here, of course these two will cancel one another out, yeah? But let's say there is a component of the force here. Let me redraw this one. I believe it would be best if I redraw this. How about if I redraw somewhere where we have enough space? All right, let me redraw it here. So we have a pendulum here. Okay, stay with me. We have a pendulum here. So here's the string, and of course, the pendulum would be swinging back and forth, of course, you can see at these locations here. So here we have mg, yeah? That is mg. And of course, we will have components of this. So this is going to be mg cosine theta, okay? And then this is going to be ft, tension force. So these two will cancel one another out, but of course, we will have another component, yeah? If this is the, let's say, the path, right? Or the circle, the curve where the amplitude is moving on, the circular path, of course, then this component of the gravitational force, which is tangent, you can see, to the circle or to the path, would restore the pendulum or this bob back to the equilibrium position. So this one is going to be mg, let me erase this, is going to be what? Is going to be mg sine theta. So this, or you can call it fg sine theta, that is also correct, yeah? So this component of the gravitational force, which is tangent to the circular path, would be the restoring force for the pendulum. So going back to the choices now, what is the correct option here? It says the total weight of the bob, that is incorrect. The component of the bob's weight tangent to the motion of the bob, that is the correct answer. And of course this says the component of the bob's weight perpendicular to the motion, that is not, because this will be cancelled by the tension force. The elastic force of the stretch string, and of course we don't have it here because the question is not, or this string is not elastic in this case. Or even if it was elastic, this wouldn't be the force that is restoring the bob. Which of the following does not affect the period of the pendulum? Once again, in order to answer these questions, write the equation for the period of the pendulum. The period of a pendulum, 2 pi square root of, let's say, length of the pendulum or the string divided by the gravitational free fall acceleration, you can say. Okay, so it says the length of the string, it depends on the length, yeah? The mass of the pendulum, there's no mass in the equation, so we can say the period does not affect or will not be affected by the mass. The free fall acceleration, of course, it is in the equation, so it would affect that. All above it is, so this or D is also incorrect. Okay, so the correct option here would be option B. Now, question 8 says, if the pendulum completes exactly 12 cycles in 2 minutes, what is the frequency of the pendulum here? So how do we answer questions like this? Remember, we said to answer the question here, frequency will say number of waves, okay, divided by what? Divided by the time here. So, but how many waves do we have? It says completes exactly 12 cycles. So how many waves do we have? 12, okay, in 2 minutes. Remember, we're not using minutes, so use or convert minutes to second. Each minute is 60 seconds, so it's going to be 12 divided by 2 times 60, that is 120 seconds, yeah? And of course now you will get an answer of what? Of 0.10 hertz. That'll be the frequency. You do the math, you'll get 0.10 hertz, and that is the frequency here. For question 9 says, if the pendulum's length is 2 meters and the acceleration is 9.8 meters per second square, how many complete oscillations does the pendulum make in 5 seconds? Now, this is also very interesting here, yeah? So let's see and answer this question. And of course, we can answer this question in 2 different ways, yeah? Okay, so let's move this up a little. How about if I just minimize this and do the math at a size? Okay, so now, once again, what do we have? We have length. We have the acceleration, says how many complete oscillations the pendulum makes in 5 minutes, yeah? So remember this, in order for complete oscillation, that means basically the number of waves. And when do we have, or where do we have the number of waves? We do have the number of waves in the frequency equation of frequency. So frequency, we said number of waves, yeah? Divided by what? Divided by the time. That is one way to say, yeah? But do we have the frequency now? So how about we find the frequency first? We'll say the period here. If we know the period, of course, we can find the frequency. So period equal to 2 pi square root of what? Length of the pendulum divided by gravitational acceleration. So period again, right? 2 pi square root of, what is the length of the pendulum? The length is 2 meters, yeah? Gravitational acceleration, it is 9.80 here. So once you do the math, you will get period equal to what? Period equal to it is about 2.84 seconds, of course. This is the period, yeah? Now, this is the period for one oscillation, remember this. So there's 2 ways to do this. One of them is if we have 5 minutes, yeah? Of course, we need to convert 5 minutes to seconds. So 5 times each minute is 60 seconds. So of course, we'll get 300 seconds, yeah? So we have a time of 300 seconds, but each oscillation, each vibration takes about 2.84 seconds, yeah? So of course, once you do the math, you'll get an answer of 106 hertz, yeah? That is one way to do that. So we found the number of, or the period for one oscillation, and then we have 5 minutes. 5 minutes, convert to seconds, 300 seconds. So in 300 seconds, how many, let's say, 2.48 seconds do we have, yeah? 2.84 seconds do we have. In another way, 300 divided by 2.84 seconds, you'll get about 106 cycles or vibrations, you can say. That is one way. Another way is this. We said we have the number of waves in frequency, yeah? So now we can find the frequency, yes? Frequency, basically, first, let's find the frequency. So frequency equal to 1 over the period, yeah? So basically 1 over the period. What is the period? That is basically 2.84, yeah? Then of course, once you do this, you will find the frequency, and then the frequency is going to be what? The frequency is going to be 0.352, yeah? That is going to be hertz as well, okay? Now, we're going to use this one to find the number of what? the number of 0.35. We're going to use this one to find the number of waves. Now I'll write this one here. So here's what we have. So frequency 0.352 equal to number of waves, you can say, or oscillations here, divided by the time. But what time do we have? The time is 5 minutes. We said if you convert 5 minutes to second, you will get 300 seconds. Once you cross multiply, so one more time. So basically number of cycles or oscillations, right, equal to 300 times 0.352. That is also another way to do this, and of course you'll get about 106 hertz, yeah? And this is how you can find the answer there. But I believe the other way is way easier. Just find out the time for one oscillation and then divide 5 minutes by that number. You'll get a total number of complete oscillation. What if they want to? What if they change the question and say, for example, how many times does it pass through the equilibrium? We know that in every cycle, it passes through the equilibrium twice, so 106 multiplied by 2. What if they say how many amplitudes do we have? In every cycle we have 4 amplitudes, so 106 in this case would be multiplied by 4, and of course you will get these answers that you see on the screen. Okay, now another question here says base your answer to question 10 to 12 on the graph below here. So use this graph to answer the following question. What kind of wave does this graph represent? Is it transverse wave? Is it longitudinal, electromagnetic, and a pulse wave here? You might choose or say electromagnetic. It is true this might represent electromagnetic, yeah, but not all electromagnetic look like this one here, you can say. Or we can have a mechanical wave, like waves of water that look like this, ocean water waves, let's say, or ocean wave that look like this, yet they are not electromagnetic, yeah? Or in another way, you can say these are all types of this, or you can say all electromagnetic look like this, but not all these sort of wave can be electromagnetic. Yeah, so we can say it is transverse wave. Transverse wave is more general. It is a wave that looks like this one exactly. Remember, we have longitudinal and transverse. Yeah, longitudinal is like a spring, a coil of spring that moves back and forth, but a transverse moves up and down like water waves. So this one is transverse wave. Longitudinal is part of, or you can say one type of transverse wave. Which letter on the graph is used for the wavelength? You do know that, yeah? From crest to crest, trough to trough is the wavelength. So letter C here would represent the wavelength. Okay, which letter on the graph is used for the trough, yeah? So letter A would represent the trough. Remember, trough would be the bottom, crest would be the top. So B would be the crest, A would be the trough or the bottom. What about letter D here? Letter D, of course, it represents the amplitude. Which letter of the graph? Yeah, we went through this one here. All right, and okay. Base your answer to question 13 to 14 on the passage below. Yeah, we have a wave with an amplitude of 0.75 and meter, of course, meter has the same wavelength as a second wave with an amplitude of 0.53 meter. The two waves interfere. So we have two waves, okay, and they have the same wavelength, okay, but of course different amplitude. When we say same wavelength and different amplitude, that is going to be a wave like this, let's say, okay. This is one wavelength. The other one, for example, one of the amplitude is bigger than the other one, okay, but they have the same wavelength. It says, what is the amplitude of the resultant wave if the interference is constructive? If it is constructive, let's say amplitude 1, this is going to be amplitude 2, so we're going to add this to, yeah, we'll get a resultant, and the resultant is going to be the combination of the two together, yeah? So this resultant would be A1 plus A2, which in this case 0.75 plus 0.53, you get 1.25 meter. What is the amplitude of the resultant wave if the interference is destructive? If it is destructive, we're going to subtract this to, yeah? And here's what you see. Instead of adding, we'll subtract them. And by the way, when we say subtract them, of course, one of them is in opposite sign. So here's the subtraction. So of course you get 0.22 meter as a resultant. Okay, now for question 15 here, it says two successive crests of a transverse wave are 1.2 meter apart. 8 crests pass a given point every 12 seconds, what is the wave speed? Yeah. Remember, in order to find wave speed, what information do you need? Yeah. Wave speed equal to frequency times the wavelength. Yeah. Now it says what? Two successive crests that are on the wave that are 1.2 meter apart. So if we have, let's say, so here's one crest and this is two. So this two is 1.2 meter apart, and we do know that this is the wavelength. Okay, so we do have the wavelength, which is 1.2 meter. What about the frequency? It says what? 8 crests pass a given point every 12 seconds. So in order to find the frequency, we did learn that frequency equal to number of waves, right, divided by the time. Yeah. Here says how many crests are passing? 8 crests, so 8 divided by the time in how many seconds? In 12 seconds. So 8 divided by 12, of course we get 0.6, yeah? So 0.666, and then it continues, multiply by the wavelength, you get the wave speed as you can see here. So wave speed, frequency times the wavelength, here's the answer that you get, which is about 8 meter per second. All right. And then we have some other questions, short responses. Question 16 says, green light has a wavelength of 5.220 times 10 to the power negative 7 and a speed of 3 times 10 to the power 8. Calculate the frequency and the period of this green light. Okay, you do know that because it is about light, so we can use C instead of V, which is also fine. Frequency times the wavelength, or you can say V equal to frequency times the wavelength. Makes no difference. We have the speed, we have the wavelength, find the frequency. Yeah? So frequency equal to speed of light, basically, because it is light, and then divided by the wavelength here. Okay, you can find the frequency. So, and then once you find the frequency, you can find the period, because period equal to 1 over the frequency. So whatever the answer is here, plug it in here. Of course, you will find the period as well. Okay, the next one says, question 17, what kind of wave does not need a medium through which to travel? We did mention that we have mechanical waves and let's say transverse waves and electromagnetic wave, let's say. So mechanical waves need a medium, obviously, to travel through. Without a medium, they cannot travel through. Like sound waves, like water waves, let's say. Yeah? But then we had electromagnetic waves on the other hand. Electromagnetic waves need no medium to travel through, just like they travel through the sun or from the sun through empty space to the earth. Yeah? So they don't need a medium. What type of wave? Electromagnetic waves need no medium. Okay, now question 18 says, list 3 waves that could form standing waves on a 2 meter string that is fixed on both ends. Yeah. So remember, we had a question similar to this previously before. Yeah. So we said, let's say in order to do this, of course, we must have complete number of antinodes. Yeah. So we can. The length is 2, so here's the equation. Remember, 2 times the length divided by the number of antinodes. Yeah, we can go with 1 antinode, 2 antinode, and 3 antinode, and all of that. Yeah, and then of course the number or the answers you get, these are going to be the wavelength that are able to create standing waves on a string that is 2 meter long. Okay, and then I believe we've solved this question before. If not, go back to the previous questions. Okay. Basically, we're using, let's say, the period to find the length of the citadel, I believe. Yes, or the lighthouse. Yes. And take a look at this one. It says, a harmonic wave is traveling along a rope. The oscillator that generates the wave completes 40 vibrations in 30 seconds. So we have number of vibration and we have the time. So what can we determine? What can we find using this 2 information? Okay, that is one. Then it says, given a crest of the wavelength, all right, or the wave travels 425 centimeter along the rope in a period of this much. What is the wavelength shown? And of course, show all the work, let's say, or show your work in general. All right, now let's do this one as well. So first of all, it says, what is the wavelength? Yeah. Now, we know that speed of the wave equal to frequency times the wavelength, yeah? So basically find the wavelength. Wavelength equal to speed divided by the frequency. Okay, now what about the first information that is given? Says the oscillator generates the wave completes 40 vibrations in 30 seconds. So basically we can find frequency using this, yeah? So frequency normally, let's write this one nicer. So frequency equal to what? Equal to number of waves, right? Divide by what? Divide by the time. So how many vibrations does it generate? It generates 40 vibrations. In what time? In a time of 30 seconds. So you divide the two, of course, you'll get the frequency, and frequency is going to be about 1.33, yeah? That is going to be hertz. So now we have the frequency. What about the wavelength? Now in terms of wavelength, it says what? A given crest. So if we have a wavelength here, so one of the crest here, it travels what? It travels 425 centimeter in a period of 10 seconds. So this one, or this crest, moves a distance of 425 centimeter in 10 seconds. So can I use this to find the speed of the wave? The answer is yes, yeah? So for the speed of the wave, we can say what? We know that speed equal to distance over time, yeah? Distance over time. Here, the distance that is traveled by the crest, yeah? So we can say crest distance divided by the time here. Or in another word, 425, we can say 425 centimeter. By the way, we can change the centimeter to meter, all right? We can find the wavelength in meter, or we can keep it as it is in centimeter, but then the result we will get, the wavelength, will be in centimeter as well. So in this case, 425 divided by 10 seconds, that is going to be 42.5, yeah? So 42.5, now we can, 42.5 centimeter per second, by the way. So now we can find the wavelength. 42.5 divided by the wavelength, which was 1.33, I believe. Okay, as you can see over there, and here you can see as well, then you'll be able to find the wavelength. If not, okay, but we normally find this one in meter, so how about we just convert this one to meter, yeah? I believe it would be best if we do that in meter. So if it is in meter, so you don't say, Mr. Y didn't find this in meter. If you do this one in meter, 400, let me start with this. 425 divided by 100, you'll get this in centimeter. So it's going to be 4.25 meter, yes? And then if you divide this one by 10, 4.25, divide this one by 10, you'll get 0.425 in meter. Now you can plug this wavelength into the equation. Oh no, this one. So let's plug in this into the equation. So 0.425 divided by the speed. My bad, what did I do? Yes, speed divided by the frequency. So here's the speed, okay, divided by the frequency, then of course you will get the wavelength, and the wavelength will be in this case equal to 0.320, that is in meter now, remember, okay? If you keep the other number or the other method that we've used, you'll get this one in centimeter, but we've converted meter to centimeter to meter, so the answer you will get now is in meters. All right, what else do we have? Now we have chapter summary, of course. Try to go through the chapter summary. I believe it is very important because it gives you a summary of the entire chapter. It saves you a great amount of time, in my opinion. Now it is time to solve a few questions of the Pass Wizari or national exam questions. The first one says, it is the maximum displacement from the equilibrium position. That is easy enough. Maximum displacement from the equilibrium position, that is the amplitude, which you do know that. If the period of the oscillation mass spring system is 4 pi second and it is mass is 48, what is the spring constant? Yeah. Now I'll write the equation for you, but I'm not going to do it. Okay. Then I'll just give you a tip to how to solve this one. It is a mass spring system. Don't forget. Okay. So don't write the equation of the pendulum for me. So in this case, of course, the period equal to 2 pi the square root of what? Of mass over the k. We want what? We want the spring constant. So in order to do this, you will have, by the way, you have the period, yeah, which is 4 pi second. You do have the mass, which is 48. We want k, but remember, in order to do this, you have to square both sides, okay? And then you'll have to square this 2 pi, and then of course, then you will be able to find the spring constant. Okay. Now, here says, what is the length of a simple pendulum? Right. Once again, I'll write the equation, but I'm not going to solve for you. So it says, if we have the frequency, all right, and then the gravitational acceleration. So remember, we want the length. In order to find the length, remember, we have length in the period equation. So period equal to 2 pi, the square root of length over gravitational acceleration, let's say, or free fall acceleration here. So we're given, it says find what? Find the length, yeah? But we're given the free fall gravitational acceleration, let's say. Okay, but do we have the period? No, we don't, yeah? We don't have. So, but instead of the period, you're given something else. You're given the frequency. So you're going to use the frequency to find the period. So period equal to 1 over the frequency. So now using this, you will have the period. So you have the period, you have this, and now you can find the length of the pendulum. Okay, now it says which one of the, this one is easy enough. What is the restoring force in a mass spring system? Remember, we said it is it elastic, weight, frictional, or both B and C? That is elastic force, yeah? Okay. And then if the amplitude, by the way, take a look. If the amplitude of the oscillation of the object is L, what is the object's total displacement during a full cycle? Let me do this one again, right? For what? For a pendulum, yeah? Or yes, oscillating object, amplitude, okay. So it could be a mass spring system that doesn't make any difference here. So let's say, here's an object, yeah, it is oscillating. So it starts at point A, goes to point B, and then all the way back to point A, yeah? So if this amplitude is L, okay, what is going to be the total displacement? So 1L starting from this point to this, so 1L to go, yeah? Another L here, starting from there. Another L to go back to equilibrium, and another L to go back to this one. So how many L's do we have? That is a total of 4L, or total displacement of 4L. Okay, and then the other questions, these are very easy, as you can see. Okay, try to solve this one as well. Okay, this is vibration of the object, let's say an object about equilibrium position in which the restoring force is proportional to the displacement. In the previous or earlier of this video lesson, we did talk about this one, yeah? We said, I don't want to tell you the answer, but we did, yeah, the component of a force, you can say. Or for simple harmonic motion. Okay, I just think I've said it. Now, the mass is attached to, these are easy, right? I want to do or emphasize on this, this is very tricky. It says the mass attached to a spring vibrates back and forth about the equilibrium position, maximum displacement, about the equilibrium position. At maximum displacement, the restoring force and dash, yeah? So we have a mass, let's use this. We have a mass that is oscillating, yeah? About the equilibrium. So here's x is 0, that is equilibrium position. So a mass attached to the spring moves back and forth, okay? Says about the equilibrium position. At maximum displacement, the restoring force and this, okay? So at maximum displacement, that is here, yeah? If this is maximum x, okay? So at maximum displacement, we know that the restoring force, okay? Restoring force and dash are what, okay? The first one says, so remember, when it says the restoring force, so F and what else is equal to this, yeah? Remember this. It says, the speed reaches, it is maximum. Can we put speed and then maximum here? Can we say these two are correct? It is true that the force is maximum, but can the speed be at maximum? The answer is no, so not option A. What about option B? The speed reaches 0 here, okay? So can we say the speed reaches 0? It is true that the speed is 0, but here says the restoring force and the speed is 0. Can we say these are both 0? This one is also incorrect, so we cannot choose this one. Remember, because it says 2, the restoring force and this. So it has to be both together then equal to, this one says the speed reaches 0. Once again, it is true the speed is 0, but can we say both are 0? The answer is No, so not option B. It says the acceleration reaches maximum. So here, now we can add, where's this? Okay. So acceleration says both the restoring force and the acceleration is maximum. Is this both correct? So the force is maximum, the acceleration is maximum. So we can say option C is the correct one. What about D? It says the acceleration reaches 0. That is incorrect. So this one is a bit tricky because it has to be both, whatever the restoring force and this, both has to be either maximum, 0 or 0. There is only one option that is correct, and that was option C. Okay, the rest is easy. You can see these are easy. Okay, let's see. It says, what is the restoring force in a pendulum? We went through this, or we talked about this previously before. Which of the following properties of a simple pendulum would change if it taken from the Earth to the Moon? Yeah? Watch this. This is very important. Says properties of a simple pendulum would change if taken from the Earth to the Moon. Remember, now once again, period of a pendulum equal to 2 pi the length over, let's say, gravitational acceleration of a free fall. Will the mass change? No. Will the length change? Will the equilibrium position change? Of course. What about the restoring force? Oh, this is very important, by the way. I thought the question would be about the period, but it's not, yeah? So for a pendulum, remember this, yeah? If this is the pendulum here, we said there is mg, okay? So there is mg cosine theta. This would be basically cancelled by forced tangent. So there is mg sine theta, or you can say fg sine theta. This fg sine theta is basically the restoring force. If we take this one to the Moon, the gravity is weaker on the Moon compared to the Earth, yeah? So of course, the restoring force will be affected. Will the mass change? We know the mass doesn't change. What about the length? The length of the string doesn't change. It's not something that is flexible. We can extend, stretch, or compress. No. The equilibrium position also doesn't change. What it changes is the restoring force, okay? So the restoring force will be weaker in this case. Okay. Now, of course, we went through this one as well. It's easy. Okay. Two waves interfere constructively. If the amplitude of one of them is A, then the amplitude of the resultant wave is, what is it? Can we say a square? That is, no, not true. It's going to be 2a, yeah? Because once again, if the amplitude of one of them is a, the amplitude of the resultant wave is two-wave construct. Okay, so it's going to be, of course, 2a, assuming that each one of the wave has a, let's say, an amplitude that is 1a, yeah? So the resultant is going to be 2a. Okay, the distance between two consecutive nodes on a standing wave, you can say, is going to be half a wavelength. We mentioned this one before. Okay, let's see if there is any other questions that are interesting to do. Now, the SI unit of a string of a spring constant, yeah? Remember, how do we know which one is the correct one? If not, easy. Make no mistakes. F of spring, of course, equal to negative kx, yeah? So k here equals to F over x, yeah? In another word, F, that is Newton, x is going to be meter, yeah? So do we have Newton over meter? And yes, and that is, of course, option A, you can say. All right, and then let's solve one more question, perhaps, and then, of course, we'll end up right here. It says, the figure shown here shows the stretched string vibrating if the wavelength of the wave on the string is 1 meter. What is the length of the string here? So remember this. It says what? The figure shows the stretched string if the wavelength of the wave on the string is 1 meter. So what is the length of the string? Remember here, yeah? So the wavelength there, you can see here, if we start from this point, the distance, let me choose a different color. Let's use blue. Okay, take a look. The length of, it says, what is the length of the string? Yeah. So watch this. The wavelength here is 1 meter. So you can see here, if the wavelength is 1 meter, so what do you think the length of the string here? So in this case, you can see that the length of the string is equal to 1 wavelength, yeah? So if the wavelength is 1 meter, so what is the length of the string? Of course, that is also 1 meter as well. And then of course you can solve the other questions or the rest of the questions, and of course you can then afterwards you can compare your answer to the answer that is provided here just to see how well you did it, okay? And then I hope you do well. Best of luck. Inshallah, next time we'll start with chapter 4, which is about sound. Sort of related to this, but of course we'll talk about some other properties of sound or some other information that is very interesting or we might perhaps encounter in our daily life. Until then, keep practicing and I'll see you soon. Assalamu alaikum wa rahmatullah.